I'm delighted to have you as part of this community. Welcome, welcome, welcome. Greetings, explorers of knowledge. Join us as we embark on a quest to understand Chasles' theorem kinematics. In kinematics, Chasles' theorem, or Mozzi-Chasles theorem, says that the most general rigid body displacement can be produced by a screw displacement. A direct Euclidean isometry in 3 dimensions involves a translation and a rotation. The screw displacement representation of the isometry decomposes the translation into 2 components, one parallel to the axis of the rotation associated with the isometry and the other component perpendicular to that axis. The Chasles theorem states that the axis of rotation can be selected to provide the second component of the original translation as a result of the rotation. This theorem in 3 dimensions extends a similar representation of planar isometries as rotation. Once the screw axis is selected, the screw displacement rotates about it and a translation parallel to the axis is included in the screw displacement. Get ready to immerse yourself in the world of planar isometries with complex numbers as we examine its impact and relevance. Euclidean geometry is expressed in the complex plane by points px where I squared is. Rotations result from multiplications by cos t sin t. Note that a rotation about complex point P is obtained by complex arithmetic with these pp's, where the last expression shows the mapping equivalent to rotation at 0 and a translation. Therefore, given direct isometry Z's, one can solve but to obtain P as the center for an equivalent rotation, provided that provided the direct isometry is not a pure translation. As stated by Cederberg, a direct isometry is either a rotation or a translation. Get ready for an enlightening exploration as we dig into history and understand its role in the broader context. The proof that a spatial displacement can be decomposed into a rotation and slide around and along a line is attributed to the astronomer and mathematician Giulio Mozzi 1763. In fact, the screw axis is traditionally called As di Mozzi in Italy. However, most textbooks refer to subsequent similar work by Michel Chasles dating from 1830. Several other contemporaries of M. Chasles obtained the same or similar results around that time, including Giorgione, Cauchy, Poisson, and Rodriguez. An account of the 1763 proof by Giulio Mozzi and some of its history can be found here. The time has come to unravel the secrets behind proof and gain a deeper understanding. Mozzi considers a rigid body undergoing first a rotation about an axis passing through the center of mass and then a translation of displacement d in an arbitrary direction. Any rigid motion can be accomplished in this way due to a theorem by Euler on the existence of an axis of rotation. The displacement d of the center of mass can be decomposed into components parallel and perpendicular to the axis. The perpendicular and parallel component acts on all points of the rigid body, but Mozzi shows that for some points the previous rotation acted exactly with an opposite displacement, so those points are translated parallel to the axis of rotation. These points lie on the Mozzi axis through which the rigid motion can be accomplished through a screw motion. Another elementary proof of Mozzi-Chasles theorem was given by East T. Whittaker in 1904. Suppose A is to be transformed into B. Whittaker suggests that line AK be selected parallel to the axis of the given rotation, with Kelvin the foot of a perpendicular from B. The appropriate screw displacement is about an axis parallel to AK such that Kelvin is moved to B. In Whittaker's terms, a rotation about any axis is equivalent to a rotation through the same angle about any axis parallel to it, together with the simple translation in a direction perpendicular to the axis. Get ready to uncover the mysteries surrounding calculation as we navigate its intriguing terrain. The calculation of the commuting translation and rotation from a screw motion can be performed using IBGA 3.0.1, the geometric algebra of the Euclidean space. It has 3 Euclidean basis vectors AI satisfying AI1 representing orthogonal planes through the origin, and 1 Grassmannian basis vector E satisfying E0 to represent the plane at infinity. Any plane a distance from the origin can then be formed as a linear combination sum I aim of I delta of y is normalized such that a 1. Because reflections can be represented by the plane in which the reflection occurs, the product of two planes and B is the biflection AB. The result is a rotation around their intersection line AB, which could also lie on the plane at infinity when the two reflections are parallel, in which case the biflection AB is a translation. A screw motion south is the product of four non-collinear reflections, and thus S-obt. But according to the Mozzi-Chasles theorem, a screw motion can be decomposed into a commuting translation T1 of web is the axis of translation satisfying 0, and rotation cosine web is the axis of rotation satisfying 1. The two bivector lines and are orthogonal and commuting. To find T and R from S, we simply write out south and consider the result grade by grade a beginner linear south tri alpha b a beta b under brace cos beta a textskler under brace a sin beta b 2 for cos beta b a text bivector under brace alpha sin beta b1 b a text quadrivector and linear because the quadrivector part is itera and 0. T is directly found to bet equal 1 fracal angle strangle and thus A equals south T equal T south frac thus. For a given screw motion south, the commuting translation and rotation can be found using the two formulae above, after which the lines and are found to be proportional to it and O respectively. In the upcoming section, we'll be shining a light on other dimensions and fields. The Chasles theorem is a special case of the invariant decomposition. Don't forget to hit that notification bell so you never miss an update from my channel.